Alright, so in this video I'm going to be explaining another important paper with the title Convolutional Kernel Networks for Graph Structured Data. This ICML paper in 2020, which is very similar to this paper in WWW 2021. We introduced a family of multi-layer graph kernels and established new links between graph convolutional neural networks and kernel methods. Our approach generalizes convolutional kernel networks to graph structured data by representing graphs as a sequence of kernel feature maps, where each node carries information about local graph substructures. On the one hand, the kernel point of view offers an unsupervised, expressive, and easy to regularize data representation, which is useful when limited samples are available. So graph kernels are very important, and we consider graph kernels that perform pairwise comparison between local substructures centered at every node. So we have two graphs G and G prime. The kernel is just this, and we use K-base to compare a set of local patterns centered at node U and U prime. And we will omit the notation in the rest of the paper. So the base kernel is just this K-base of U and U prime. Also, you can create a different way for these base kernels. You can design differently. Since computing all path occurrences between graphs isn't hard, it is possible instead to consider path of length k, which can be reasonably enumerated if k is small enough or the graphs are sparse. Then we may define the kernel like this, where a here is represents attributes for path p, and delta is the Dirac kernel. It is also possible to define a variant that enumerates all paths up to length k by simply adding the kernels. So one may consider using walks by simply replacing notation by W in previous definitions. A subtree is a subgraph with a tree structure. It can be extended to subtree patterns by allowing nodes to be repeated, just as the notion of walks extended that of path. It is essentially based on a mechanism to augment node attributes by iteratively aggregating and hashing the attributes of each node's neighborhoods. After I iterations, we denote by A sub I the new node attributes, which is defined in algorithm 1. So for two graphs, KWL and K subtree, you see the subtree and the attributes capture subtree patterns of depth I rooted at node U. Now they define this graph feature map, which given a graph G and a reproducing kernel Hilbert space, a graph feature map is mapping phi which associate to every node a point in Hilbert space, representing information about local graph substructures. For example, the kernel associated to maps phi and phi prime for two graphs is defined like this. Even though graph features phi and phi prime are graph dependent, learning with K is possible as long as they all map nodes to the same reproducing kernel Hilbert space. We show that now detail the full construction of the kernel, starting with a single layer. We propose a single layer model corresponding to continuous relaxation of path kernel. We assume that the input attributes such that G admits a graph feature map. We rely on paths of length k and introduce the kernel k sub 1 for graphs G and G prime with feature maps phi 0 and phi 0 prime. And it denotes the concatenation of k plus 1 attributes along path P and this is an extension of path kernel. So we go from feature maps to graph feature maps. The kernel k sub 1 or kappa sub 1 acts on pairs of paths in potentially different graphs, but only through their mappings to their space h k plus 1. Since kappa 1 is positive definite, we denote by h1 its reproducing kernel Hilbert space and consider this now phi 1, the phi 1 map. We can define a graph feature map operating on nodes. So this is a construction of graph feature map. The first step extracts path of length k from node U, then maps them to RKHS via Gaussian kernel mapping. Then they use Nystrom method and single layer model. Because a naive computation of the path kernel k sub 1 requires comparing all pairs of paths in each pair of graphs. To gain scalability, a key component is the Nystrom method, which I have explained in a different video. Very old idea, computes finite dimensional approximate kernel embeddings, and we discuss here the use of such a technique to define finite dimensional maps. The consequence of such an approximation is that it provides a finite dimensional approximation. Then a supervised learning problem with kernel k sub 1 on dataset where y sub I are labels in R can be solved by minimizing the regularized empirical risk. So the Nystrom method projects points from a given RKHS onto a finite dimensional subspace and performs all subsequent operations within that space. Now we define this subspace which spans phi1 of z sub 1, z sub q. Given a new path with attribute z, it is possible to show that projection of path attributes onto this span leads to Q1 dimensional mapping. And these are Gramian matrix, the entries of the Gramian matrix. And then the approximate graph feature map is just pooling all of these. Now, this is important for interpretation as a GNN. When input attributes have unit norm, which is the case of if we use one-hot encoding, the Gaussian kernel may be written like sigma 1 of z transpose z prime, which is a dot product kernel with a nonlinear function sigma 1. So calling z in R the matrix prototype path attributes, now we have psi 1. So map of psi 1 is built from psi 0. A useful consequence is the possibility of optimizing filters of z with backpropagation. So this is a forward passive multi-layered GCKN that we compute the size and then the pooling of them, so we have this representation. Now we can express more complex structures, which requires breaking the successive linearities that introduced. So this effect can simply be obtained by using a second layer with path length K2. And then they create a multi-layer version of that. But one can use a relaxed walk kernel instead of path kernel in 8 at the cost of losing some expressiveness but gaining some time complexity. So this paper in 2019 introduced an approach to interpret trained GNN models by finding a subgraph of an input graph G, maximizing the mutual information with its predicted label. We call GCKN path our model size of 1 with a single layer, GCKN sub 3 our model size 2 with 2 layers. So as these models are built upon path enumeration, we extend the method of Ying 2019 by identifying a small subset of a path in an input graph. So the problem becomes like this, and here pk.m denotes the use of m of p, a of p, instead of just a of p in the computation. So they did experiments on these data sets, and they compared classification accuracies of popular models like graph convolution to this model, which you see some improvement, very, very little improvement. And these are motifs extracted in the mutagenicity dataset. You can find this in mutagen dataset in PyTorch geometry. Again, mutagen dataset, because mutagen dataset is very good if you have an interpretable algorithm